So today's topic is tensors. We are going to learn how what tensors are, uh, how to express tensors in various coordinate systems, what are the tensor transformation rules, and then finally calculus of tensors. And we will um, discuss as much on these topics as it is required for our course mechanics of fluids. So I want to start with my attempt to answer this question, what are tensors? A tensor of order n in an m-dimensional space is a mathematical object comprising of m raised to the power n numbers, which depend on which the numbers depend on our working coordinate system. However, note that the tensor as a mathematical entity is defined to be invariant to the choice of any coordinate system. This invariance of the tensor to any coordinate system is ensured by a set of rules which we call the transformation rules of tensors. The m raised to the power n numbers, which are also called the scalar components of the tensor, must follow these transformation rules when we switch from one coordinate system to another. When we try to express the tensor in one coordinate system, and at a later time when we are trying to express the same tensor in another coordinate system, then the scalar components must be related. The tensor components in two different coordinate systems must be related through what we call as the transformation rules of the tensors. Now these things will become more clear as I elaborate on each aspect of what I had on the previous slide. For us, these people who are trying to learn fluid mechanics, we will be dealing with quantities. We will be dealing with quantities which are relevant in the three-dimensional space in which we exist. So for us, m will be equal to 3. As engineers, for us, m will be equal to 3. In this space, for example, velocity of a particle is a tensor of order 1. So little n is equal to 1. So in any working coordinate system of our choice, velocity will have 3 raised to power 1, 3 scalar components. Another example of a tensor is a stress at a point, and this quantity is a tensor of order 2 with n being equal to 2. So in any working coordinate system, a stress tensor will have 3 raised to the power 2, that is 9 scalar components. A tensor of order 1 is also called a vector. However, tensors with their orders greater than or equal to 2, there is no special name. We simply refer to that tensor as tensor of order n. Density of a fluid, another example, is a tensor of order 0. So it will have n equals 0, and accordingly it will have 3 raised to the power 0, that is 1 scalar component. Now tensors of order 0 are also called scalars. Now in fluid mechanics, like other branches of science, we will come across tensors of order 0, of course, scalars, order 1, order 2, and even tensors with their order being more than 2. Especially when you go to turbulent flows, we come across tensors of order 3, 4, and so on. So that is why it is important for us before we start fluid mechanics to have some basic concepts about tensors. Now let's talk about how to express a tensor in a coordinate system of our choice. So let us have a Cartesian coordinate system which I am showing here on this slide. You have uh, the coordinate system that I have, I denoted by this long string of alphabets and numbers as O, X1, E1, X2, E2, X3, E3. Here O is, this letter is telling me that that is the origin of the coordinate system. E1, E2, E3 that appear in that string of characters, they represent the three mutually perpendicular unit vectors. X1, X2, X3, which are appearing here, they are the coordinates of an arbitrary point P in space. Now, if I have a tensor T, say it has order 1, so it is a vector, how do I express that tensor of order 1 in this coordinate system? Now note that in this course, all tensors of order greater than or equal to 1 will be represented by an alphabet with an underbar, like what I am showing here, V underbar or Q underbar. Even when, say, V is a vector, even then I will use an underbar here. And even when Q is a tensor of higher order, say order 3, I will still denote it with an underbar. Now this is different from some textbooks in which you see that the author represents a vector with an overbar or an arrow on the top of the symbol, whereas for higher order tensors they still use an underbar. So I am not going to make any distinction. For me, any tensor which is not a scalar, it will be denoted by an alphabet and an underbar. So coming back to that tensor T, I want to express that in the Cartesian coordinate system. I would write this as T1E1 plus T2E2 plus T3E3, where T1, T2, T3 are the scalar components of the tensor T in our given coordinate system. So we see that we have three scalar components, and that I can write as 3 raised to power 1 because I'm trying to remind myself of the formula that I mentioned earlier, that a tensor of order n in m-dimensional space has m raised to the power n number of scalar components. So m here is of course 3. We are in 3-dimensional space, and tensor is of order 1. So that is why you have these three scalar components T1, T2, and T3. The unit vectors E1, E2, and E3, we say that they form a basis using which the tensor of order 1 has just been expressed here. As far as these components T1, T2, and T3 are concerned, we can call them, I can call T1 as the component of T along the basis unit vector E1. Similarly, T2 is the component of T, tensor T, along the basis unit vector E2. And T3 would be called as the component of tensor T along the basis unit vector E3. Note that T1, T2, and T3 themselves are just numbers, right? They are scalars. 5, 4, 0, minus 2. They can be such numbers. So now there is a question I want to ask. Do T1, T2, and T3 depend on our choice of coordinate system? The answer is yes. Does the tensor T depend on the choice of coordinate system? The answer is no. So the tensor will remain invariant. You may remember that's how I described tensor on my very first slide of this video. The tensor will remain invariant. However, its components may change as you switch the coordinate system which you are using to express that tensor. So let's look at this aspect in more detail. So I have now two coordinate systems as you see on the slide. One is the red coordinate system, which is the same as what I was using on the previous slides, and now I have another new coordinate system denoted drawn in green color, and that coordinate system shares the same origin as the red coordinate system. And in my notation of this coordinate system, uh, it, the green one will appear as O x1 prime E1 prime, x2 prime E2 prime, and x3 prime E3 prime. And note that E1 prime, E2 prime, and E3 prime are again mutually perpendicular unit vectors, and x1 prime, x2 prime, x3 prime are the coordinates of an arbitrary point P in the green coordinate system. If both x1 prime, x2 prime, and x3 prime and x1, x2, x3 are coordinates of the same point, say point P, keep in mind that in general x1 prime will not be the same as x1, x2 prime will not be the same as x2, and x3 prime will not be the same as x3. Now going back to that tensor T, and now if I try to express that tensor in the green coordinate system, I should write an expression like what I have here. T1 prime, T1 prime, E1 prime, T2 prime, E2 prime, and T3 prime, E3 prime. And in general, T1 will not be equal to T1 prime. Similarly, T2 and T2 prime and T3 and T3 prime in general will be different from each other. But then the question is, they are different, however, do we expect them to be related to each other? And the answer is yes. That relationship, or rather a set of relationships which bring together T1, T2, T3 on one hand, and T1 prime, T2 prime, and T3 prime on the other hand, is called the transformation rule of tensor of order 1. So what is that rule? Let us derive it now. But before we do that, let's have a more compact and efficient way to express tensors, because we want to save some time, effort, and space on the slide while expressing and writing several times the expression of a tensor. So recall T, I was writing the tensor T in the red coordinate system as T1, E1, T2, E2, and T3, E3, right? Why don't we write it using this sigma notation, where I have an index I, which is appearing as a subscript with T and E, and we allow I to go from 1 to 3. So I can take values alternatively as 1, 2, and 3, and this summation sign or the sigma sign tells me that I should allow I to take values 1, 2, 3 and keep adding the terms that are generated uh, after taking those values, right? So this is one way of making things compact. I write less and convey more. But why don't we go even one step further and say that we don't even write the sigma symbol. We just write TIEI and let that represent the whole expression, sum of 3 terms. This rule, which we are now making, is actually called the Einstein summation rule, and I put it like this. If an index like I is repeated 2 times, summation over that index is automatically implied, and we will not bother to write even this sigma symbol anymore. Thus T equals TI by itself represents the full tensor. Now note that if one chooses a different index, not I but j, still the meaning remains the same. So TIEI, since I is being repeated twice according to the Einstein's summation rule that I just mentioned, it means that allow I to go from 1 to 3 and add all the terms which are generated together. Now the same meaning is indeed conveyed by this expression if somebody is writing that as TJEJ. J is being repeated 2 times. You just allow J to take values from 1 to 3 and then add all the terms. So TIEI is indeed equal to TJEJ, indeed that is equal to TPEP. So you can use any alphabet to denote that repeated index. The repeated index can be any alphabet, however, ensure that that alphabet appears exactly 2 times. If an index appears once in an expression, then it will not imply summation. And if an index appears more than 2 times, then it will be meaningless because we really do not have any rule for that. Okay, so we have to be careful. Now, in some situations, if an index is appearing once, it can still make sense. But if you are writing an expression for a tensor, in that expression on the right hand side, if any index is appearing once, then there is something certainly wrong. If any index is appearing 3 times, there is certainly something wrong. Every index should appear exactly 2 times in an expression for a tensor. So for example, T equals TPEQ is meaningless. It doesn't carry any meaning. P and Q are appearing just once and we don't know what it means actually. Now let us go back to the red and green coordinate system. The same tensor of order 1 can now be expressed actually in 2 ways using the 2 different coordinate systems. First as T equals TIEI and the other as T equals TJ prime EJ prime. And because we defined the tensors to be invariant across coordinate systems, it means that TIEI must be equal to TJ prime EJ prime. Now at this point, let us think of 9 numbers which I am denoting as A11, A12, A13 and so on all the way to A33 such that these become the coefficients of the unit vectors of the red coordinate system when you are trying to write an expression for one of the unit vectors of the green coordinate system. This is what I mean. If I am trying to write E1 prime, which is a unit vector of the green coordinate system, using the unit vectors of the original red coordinate system, then I will write that as using these numbers A11, A12 and A13. Now if you pay attention to the indices here, what is happening across all these 3 terms, we have 3 A's appearing and for each one of them the first index is 1 and that is going with the index of the unit vector, prime unit vector that you are trying to get an expression for, whereas the second subscript of all these A's on the right hand side, they are matching with the corresponding unit vector of the red coordinate system. So here 1 is matching with 1 here, 2 is matching with 2 here, and 3 is matching with 3 here. So this is the definition of all these 9 numbers. So in that way, I can write E1 prime as A11 E1, A12 E2, A13 E3, which in my using the Einstein summation rule of compact representation can be readily written as A1J EJ, right? J is being repeated. J is a repeated index. It implies summation over J. And if you do that, you will recover this sum total of 3 terms that we have here in the middle of this equation number 1. Similarly, E2 prime can be written as A2J EJ and E3 prime can be written as A3J EJ. Now, if you think about it, Aij, the number Aij is actually the cosine of the angle that exists between Ei prime and Ej. And to prove it, what I can do is you go back to equation number 1 and you take a dot product of equation 1 with E2, both sides. So left hand side you will get E1 prime dot E2, right? And will that not be the direction cosine between E1 prime and E2? Indeed it will be. It will be the cosine of the angle between E1 prime and E2, right? And now let's see what happens on the right hand side. When you dot this full expression with E2, what you get is only one surviving term, and that would be A1 to E2 dot E2, and that is A1 to itself. So left hand side is clearly the cosine of the angle between the two unit vectors, and that is what is turning out to be A1 2. Okay, so in that way we can also show that E1 prime dot E1 will be A1 1 and E2 prime dot E2 will be A2 2, etc. And in general, you can write that Aij will be equal to Ei prime dot Ej, where I and j can take values from take values 1 or 2 or 3. Okay. Now here is an example in which you see there are indices appearing, and if you focus on right hand side of this equation, you have one index I appearing only once, j index appearing only once. So this is an example where an index may not appear 2 times, and since it is not appearing 2 times, there is no summation implied, but it is conveying something else. What it is conveying is, if you take I equals 1 and j equals 3, for example, it will give you A13 value. Okay. So having an index appearing once still makes some sense. It still makes sense. It doesn't imply summation, however. Now, when you are having an index appearing only once in an equation, at least make sure the following: if there are two individual indices I and j on the right hand side, on the left hand side also you should have two individual indices, or two indices appearing once exactly in the same manner. I mean, if you write APQ equals EI prime dot EJ, it will not carry any meaning. So if there are I and j on the right hand side, left hand side also you should have I and j as appearing on their own without being repeated. And when an index is appearing only once, that is also called a free index. So in that way, this equation has two free indices. On left hand side we have two free indices, right hand side we have two free indices. This should always be the case. Further, the two free indices on the left hand side must be the same as the two free indices on the right hand side. On the left hand side I have I and j as free indices. Accordingly, on right hand side I should also have I and j as free indices and nothing else as free index. So coming back to these 9 numbers, what these 9 numbers convey to us, or the information that they have within themselves, is how the two coordinate systems, the red and the green one, are oriented with respect to each other, right? Direction cosines. Now let us go back to the derivative of the transformation rule, derivation of the transformation rule. You remember T we wrote as we wrote T in the green coordinate system as T1 prime, E1 prime, T2 prime, E2 prime, and T3 prime, E3 prime. Now what I am going to do, I want to get rid of all primed unit vectors on the right hand side. And how do I get rid of them? I will get rid of them by representing these primed unit vectors in terms of unprimed unit vectors with appropriate Aij as coefficients. And we already have those formula here, 1, 2, 3. I'm going to use that to replace E1 prime by A1i Ei, E2 prime by A2i Ei, and E3 prime by A3i Ei, completely in line with what I had here as 1, 2, 3. Of course, the index j, we had repeated index j there, here we have repeated index as I, but I hope by this time we are clear that as long as they are appearing 2 times, it doesn't matter whether you have I or j. So once you have this, once you insert these substitutions in this expression, which is highlighted here, we will soon be getting what we call as the transformation rule of the tensor. So I have that. Once you make these substitutions for E1 prime, E2 prime, and E3 prime using these expressions, what we can get is this. So T I am rewriting as T1 prime, A1i Ei, A2i Ei, and A3i EI, right? And here I have put the sigma notation again, but actually it is not required, but the meaning still remains the same. So now if you group, so we will actually get 9 terms here, right? 3 terms here, 3 terms here, and 3 terms here. If we group them separately, I mean if we try to make 3 groups of terms out of these 9 terms here, such that we separate the coefficients of the even unit vector, then separate the coefficients of the E2 unit vector, and then separate the coefficients of the E3 unit vector. This is how it will look like. You see, I have first 3 terms have E1, second set of 3 terms have E2, and third set of terms have E3. Now, if you regroup them in the manner I have shown here, with coefficients of E1 collected here, coefficients of E2 collected here, and that of E3 collected here, and then if you compare this expression, long expression, with the other simple expression for T in the red coordinate system, which would be T1 E1, T2 E2, and T3 E3, that's all, then what we get is this set of relationships which are T1 equals Ti prime A I1, T2 equals Ti prime AI2, and T3 equals Ti prime AI3. So what we have essentially derived is a set of relationship between the scalar components of the tensor T in the red coordinates, green coordinate system, how they are related to the scalar components of the same tensor in the red coordinate system. And this set of 3 equations that you see here is called the transformation rule for tensor of order 1. And mind you, here again, indices are being repeated, which implies that summation is there. Okay. And then we move on, and then we ask this question, how do we express a second order tensor? A second order tensor in my Cartesian coordinate system, in the red coordinate system. Now, a second order tensor will have 3 raised to the power 2, 9 scalar components. But then E1 and E2 and E3 on their own can make a basis for first order tensors only, right? When T was the first order tensor, I wrote that as T1 E1, T2 E2, T3 E3. So 3 scalar components were accommodated by E1, E2, E3 in that manner. But now we have a second order tensor which has 9 scalar components. How do I express that? So essentially I'm saying what should be my basis for expressing a second order tensor. Now, for expressing a second order tensor with 9 components, we need a basis with 9 members, right? And this 9-member basis is formed with what we call 9 dyads. A dyad is an ordered combination of 2 unit vectors. Example, E1 hat, E2 hat. Here E1 and E2 are just standing next to each other. There is no dot product. There is no cross product. There is nothing. In this way, we can create different dyads using combinations of E1, E2, and E3. And indeed, you will get 9 unique combinations or 9 unique dyads if you use E1, E2, E3 as the unit vectors. And these are the 9 dyads, E1, 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 E2, E1, E3, all the way to E3, E3. Now, please keep in mind that E1, E2 is different from E2, E1 because order matters. This is how we are defining our dyads, that E1, E2 standing next to each other is a different dyad than E2, E1 standing next to each other. Once you have this new basis, dyadic basis made with dyad, you can express a tensor T of second order in this manner, what I have shown. So what is happening here? First of all, you see these dyads, 9 dyads appearing, and each dyad is coming with a coefficient, and that I am representing as, and that coefficient is a scalar, and I'm representing that as t, same alphabet but no underbar, because that's right now on the right hand side. These uh, these t's are scalar components, and then it takes 2 indices which match with the dyad with which this whole term is standing. So T11 E11, T12 E1 E2, and all the way to T3 3 E3 E3. And here I would written this: E1 E2 is not the same as E2 E1. Order matters. Now T12 we can call T12 as the scalar component of tensity along the dyad E1 E2 E1 E2. So I am using the words which are similar to the words I used when we were dealing with first order tensor, and we are extrapolating that idea that we had for first order tensor. So T12 is the scalar component of tensity along the dyad E1 E2. T21 is the scalar component of tensity along the dyad E2 E1. And so on. In general, note that T12 will not be equal to T21, T13 will not be equal to T31, and T23 will not be equal to T23. Sorry, T32 it should be. If you go back to your sigma notation, instead of writing T as some of these 9 terms one after another, we can in a more compact way write the entire tensor as two summation signs, Tij, Eij, where I equals 1 to 3 and j equals 1 to 3. There are 2 summations. Eij can be called the ijth dyad. So if I is 2 and j is 3, E2, E3 can be called as the two-third dyad. Now it may sound a little unusual from a grammatical point of view, but we will have to use 2 numbers because a dyad is described by 2 numbers, right? 2 indices. So in that way, I cannot call Eij as the ith dyad, or I cannot call it the jth dyad. Here both I and j are important, so I have to create this kind of a new word that Eij is the ijth dyad. Now Tij can be called as the ijth component of tensity in the chosen coordinate system, right? Alternatively, rather specifically for T12, I will call that as 1/2th component of tensity in our working coordinate system. There's some more observations we need to make here to get ourselves more familiar with this expression of a second order tensor. Note that this quantity here is not the same what I have here. And what is the difference? The difference lies in the order in which Ij is appearing here. Both have 2 summations, both have 2 dummy indices, but here we have summation Tij Eij, here I have Tji Eij. So Tij Eij double summation is indeed tensity, but Tji Eij is not my tensity. That is why they are not equal. And similarly, T will not be the same as summation over Tij Ej Ei. So whatever is the order here, that order should be retained when you write that dyad. That is the key point. If that order is disturbed, it doesn't represent T tensor. However, note that whether I appears as first index or whether j appears as the first index, that doesn't matter. For example, you see this expression, this has Tij Eij and it has Tji Ej Ei, and I will say that both are legitimate expressions for the density. So it is not about I and j. What is important is the order in which the indices are appearing as subscripts of t. That order should be retained when you write the dyad. If that order is the same, uh, then it is a legitimate expression for a second order tensor. Now let's talk about transformation rule for second order tensors. Again, I have a two coordinate system. The red one is my original coordinate system, and now I have a green coordinate system, the prime coordinate system. And in the red coordinate system, we write t as Tij, Ei, Ej, and in the green coordinate system, accordingly, I must represent that as Tij prime, Ei prime, Ej prime, right? Again, in general, Tij will not be equal to Tij prime, but the same question I raised, whether they are related. Yes, they are related by what will be called, what can be called the transformation rule of tensor of order. And we can derive it as follows. So in the green, I start with the green coordinate system. I write t as Tij prime, Ei prime, Ej prime, right? And then recall that Ei prime is AIP EP. And again, I have used the sigma notation. Even if I remove the sigma sign here, it will still carry the same meaning. But since I have it, I'm not going to change it at several places, assuming that the audience is still able to understand what I am doing. So Ei prime I am writing as AIP EP, Ej prime I am writing as AJQ EQ, and I go and substitute Ei prime by this, and I substitute Ej prime by this, and I get this expression what you have here. So now I have four summation signs in the same expression. Now mind you, here when I wrote the expression for Ei prime, of course I had I here as one index, and this is another example in which you can have an index appearing once, and it's called a free index. You may remember I said if you have a free index, the number of free indices should be the same on left hand side and right hand side, which is true here. And also the free index should be identical. On the left hand side it is I as the free index, and exactly the same should be on the right hand side, I as the free index. So it is still carrying meaning. The point I want to emphasize here that the repeated index that is coming because of a new summation here, I am writing that as P. Why am I doing it? Why am I not using I? Well, choosing I will immediately make I appear 3 times here, which we know is meaningless. So I doesn't seem like a good choice. How about J? Why I did not put it as J? Now, if you put J here instead of P, it will still be meaningful in the expression at this level. But when this is going to go and sit here, what I have done here, I hope you will see that if J has been used, if J is used instead of P, you will start having J appearing more than 2 times in this full expression, this double star expression. So I need to be careful that any new repeated index that is going to come in the expression should be anything but the indices which have already appeared in the expression. So I can choose this repeated index to be anything but not I and not J. Similarly, when I am replacing Ej prime by AJQ EQ, I am again being careful that the new repeated index, which is Q here, it should not be I, it should not be J, and it should not be P even, because P has already been taken. So it can be anything but these 3. So I have chosen a new one. So this thing you should keep in mind, because otherwise you will start having the repeated index more than 2 times, and then it will have no meaning. You will not know what to do. That is all what I have written. You should not do this because it will create confusion in right hand side of this. There is already a summation over I, there is already a summation over J in RHS of this. Thus I am using new indices for new summations. So with these substitutions, I have this expression for T in which the scalar components are primed, but all the unit vectors that are appearing, they are from the red coordinate system. And then there are 4 summations here which I can club together and write the expression as what I have here. Now, while dealing with such expressions, you have to be, you can do this kind of a periodic check as you simplify the expression more and more, that at any stage, since it is an expression for a tensor, every index should appear 2 times and exactly 2 times, not less, not more. So let's do that check. I is appearing 2 times, fine. J is appearing 2 times, fine. P is appearing 2 times, and Q is appearing 2 times. So in that way, at least from that point of view, from Einstein's summation rule point of view of that rule, we have not made any mistakes. I might have made some other mistakes in writing the order in which the indices are appearing as subscripts to quantities. That possibility is still there, but at least summation wise, for the summations to be meaningful, I should keep checking this aspect that every index should appear exactly 2 times when it is an expression for a tensor. So now after that, what I'm going to do here is I am going to group the terms in the way I have shown here, such that I have EQ outside, the dyad EQ outside, and then I have summation over P and Q on the outside of this curly brackets. Okay, and why am I doing it? Because now the next step is, if you recall how we got the transformation rule for a first order tensor, I'm following a similar line of approach. I have written this whole thing as if, I have written this whole expression in a manner such that I can directly compare it with the expression which I am calling double plus here, which is the expression of T directly being written in the red coordinate system. So directly in the red coordinate system, you would have written T as TPQ, EPEQ, right? Summation over P and Q. Now, since the tensor, every tensor is invariant to the choice of coordinate system, part of the definition, then RHS of one, RHS of this plus equation must match with the RHS of the double plus equation. And if you compare these two, you will be able to conclude that TPQ, which is appearing here, must be equal to what is all inside these curly brackets, which is Tij prime AIP AJQ. Indeed, this is the transformation rule for a second order tensor. Again, P and Q can take values 1 to 3, and accordingly you will get it expressed. You will get TPQ being expressed in terms of all the Tij of the prime coordinate system. Okay. Now, if we move on to higher order tensor, we can now extend this idea, what we learned in the context of first and second order tensors. We can extend that idea to higher order tensor. For a tensor of order 3, we will have, first of all, we realize that we will have m raised to the power, m equals 3 raised to the power 3. That means it will have 27 scalar components. And then you think about it, that to write the full expression of this tensor, we need a new basis which has 27 members. And those 27 members should be created somehow using E1, E2, and E3. How do we do this? The way we do this is shown here. So now, instead of considering 2 unit vectors standing next to each other, now you should start considering 3 unit vectors standing next to each other where order matters. And when you do that, when you try to create such new entities, you will see you can create 27 of them. Some of them I have shown here, and whatever is in between, if required, I think one can generate explicitly write that also. So I have E1, 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 first member, E1, E1, E2, second member, E1, E1, E3, third member, E1, E2, E1, and so on, all the way to E3, E3, E3. Now earlier, when I had 2 unit vectors standing next to each other, I call them dyads. Unfortunately, I do not have special name for this new combination, new entity that we have created for ourselves. I am just going to call them third order dyad. Third order dyad. So dyad for me now means, in general, in this context, in this context, in the context of a third order dyad, this phrase, dyad means a combination of unit vectors standing next to each other, and third order means there are three of them standing next to each other. These 27 third order dyads are the members of a basis which is used to express a third order tensor. Its expression in our coordinate system, original red coordinate system, would be what I have shown here. T111, even, T112, even, E2, all the way to T333, E3. So now T on the right hand side takes three indices because it has to convey it is the coefficient of which dyad, right, of the 27 possible dyads. Again, in the using the sigma notation, it can be written in this manner, what I have shown here. And again, you have to be careful that when you write this as summation over ij and k, and you write t I j k, that order has to be followed by the order in which the unit vectors are also appearing. Note that we are using an underbar to denote a tensor, and this question may come to your mind that since I have all the tensors having an underbar, how do I know which order tensor it represents? And that I said earlier also, it can be inferred from the context. And if you are expressing a tensor using a Cartesian coordinate system, you can infer the order of that tensor by looking at what order dyad is there on the right hand side. So if only EI is appearing here, it means T is a first order tensor. If there is a combination EI, EJ appearing, it means it is a second order tensor. And if it is EI, EJ, and EK, then it means that N is got to be third order tensor.